Okay, so welcome back to the masterclass. So this is going to be our last session. Sebastiano from Warwick is going to talk about this paper from Anthony Lee. So thank you very much for agreeing on presenting, Sebastiano.
All right, so a brief introduction. I don't have experience on parallel computing, so probably this is going to be a very introductory talk, and I may say wrong things. So I want you to correct me if I am saying something wrong or maybe not precise. So the way I was thinking is to sort of present this paper in a sort of reading group way. So I also didn't prepare slides. This paper is written by Anthony Lee, but also Christopher Liao, Michael Gills, Arnaud Doucet, and Christophe Holmes. And it's about the use of graphic cards, so GPUs for Monte Carlo simulation. So I have experience in Monte Carlo simulation. I don't have experience in parallel computation. And here the focus is using graphic cards. So the first things I want to highlight is so let's remember what are the difference between graphic cards and clusters. Okay, so first of all, something that maybe was highlighted by Chris yesterday, but we can just highlight again that graphic cards are in all our computers, and they're also shipped by clusters. We are lucky maybe because we are all affiliated with universities and we can use also clusters, but they are not usually as available as graphic cards. So the graphic cards, so maybe you can just write GPUs versus cluster. With cluster, I mean network computers. So the GPUs are cheaper and they are available to us, to most of us. They also don't require any maintenance, while clusters, they usually need to be maintained. So low maintenance, let's say. Then, well, an issue nowadays is also the energy consumption. And in that respect, the GPUs are much better than clusters because GPUs, they are also low energy consumption devices. And another thing you may be concerned or may not is that GPUs are in your device. So they are kind of local hardwares. You don't need to send data around. And so if you have sensible data that you don't want to send to other devices, it's also better in this respect. So they are local. All right, now some negatives of GPUs. They are, again, as mentioned yesterday, they are very specialized hardwares. They're different from CPUs. So they are quite specialized. And for example, what I mean here is that, for example, they need a host. They cannot just run things on the GPUs. They have to be hosted by a CPU. So they are not independent. They are very specialized. Also, as Chris mentioned yesterday, they don't manage data. So they cannot really infer how to store your data in an efficient way. So you need to do it manually. So no data management. And I think a part of the specialization is, for example, everybody uses single precision floating numbers rather than double precision floating number because it's much faster to do computation with single precision floating numbers. And I think this is also part of being such a specialized hardware. So something to remember is to use float 32 instead of float 64. Positives maybe. Yesterday has been mentioned already that GPUs they have very low latency, and this means low latency, which means that they are faster on accessing and writing data. So fast data access and right. And they also have what is called high bandwidth, which means that they can transfer large amount of data between between threads somehow. This is called high bandwidth. And this is again in contrast with clusters, which are usually so they are not as fast on accessing and sharing data. And here in this paper, there is a graph which I found. Oh, I need to use that. Which I found kind of nice, which is this one. So we have the GPU. The GPU has also many cores, many processors. If you compare them with CPUs. The black line is what I called before the bandwidth. So the GPU has its own memory, which is not the CPU memory, and it can access and write data on memory much faster because of its bandwidth. What is the bottleneck? Also this presentation is really nice because it's kind of stressed that the thin line between CPU and GPUs. So as long as you work on GPUs, then all is fine. But if you have to move from GPUs and CPUs, that is super slow. So you shouldn't do it. You should be careful. So this traverse move is kind of the bottleneck of when using GPUs. Right, other things here. Yeah, the CPU is called host because it's hosting the GPU, and that's it. Okay. So the first naive parallel algorithm. Yeah, sorry. So if you have any question, just ask, or if you want to say something, please interrupt me. The first maybe naive algorithm, Monte Carlo algorithm, is the important sampling. It's naive because the parallelization is really naive, is trivial. So let's just define a few objects. So we have a target density from which we want to simulate, which is pi of x, maybe on a space calligraphic x. And we want to estimate integrals with respect to some functional. So we want to estimate these objects, and we are doing it with Monte Carlo. So we estimate it with Monte Carlo samples. Let's say n. And the important sampling you probably know. We just take random variables and we weight them. And these random variables are just IID. They are from another distribution, not pi, because we cannot simulate it directly from pi. And therefore, we have this weight, which is just the ratio between, so W of x is just pi of x over Q of x. And if you take the expectation, you see that this estimator is unbiased. Its expectation is exactly this integral. And also, as n goes to infinity, its variance goes to 0. You want to put the 1 over it? Yeah, maybe let's put the 1 over it. Yeah. Right. Okay. And let's see how is it implemented with CUDA. So this paper is working with C, and in C we have to implement function in the GPU using this CUDA, which is kind of an interface for writing programs in the GPU. Now, this is the snippet, just the code for writing this important sample. What I wanted to stress here is that, so first of all, we pre-allocate the output. So the output is given as input. So we have now the input or the number of Monte Carlo sample that we want to simulate. The input array, which is, let's say, our IID random variables from a distribution through that SPQ. And then we have an output vector, which is a vector which can be initialized in any way because we're going to write on it. Okay. And we have to kind of pre-allocate all this memory because we cannot really allocate memory while running this program in the GPU. All right. The other feature is that all functions in the GPU, they need to return void, so they need to return nothing. This is so I was also trying. My aim was actually to implement a few stuff in Julia, which because I usually use Julia for implementation. You can do GPU implementation with Julia. The problem is that then I have a Mac. Which has is a chip for which there is not a good the GPU develop is not really developed for this chip, the GPU kind of part. So, but in any way, the programming part is exactly the same. So also in Julia and also in Python, I guess, all the functions need to return void. The other thing I wanted to stress in this segment of code is that there are very few allocations inside this function because we are just allocating two variables which are w and x, local variables which are floating number and one integer, and that's it. And then we are writing on stuff that are given as input. So then essentially we have a for loop which goes through some indexes, and the indexes they are unique for each thread. So at the beginning, we kind of infer which indexes we want to go through. And then we just take the input, which is the random variable, compute the weight, and spit out this product, this element in the sum. Is it clear? Okay. Now there are these other functions which are again written for GPU, which are just the functions evaluating the weights. So evaluating in this case the importance distribution is standard Gaussian is the second one. The proposal. The target is a mixture of Gaussians, and the function that we want to evaluate is the second moment, the square of x. And let's go to the main program is this one. So in the main program, we start pre-allocating. So we create a floating array in the CPU, which is the first line, this line here. Then we also pre-allocate some memory for the GPU, which is the CUDA malloc functions. Then in this program, which is very simple, you can definitely improve this important center. We generate our random variables in the CPU. Okay. So we are not using parallel computing here. Well, then what we do, which is quite slow, is to copy this array generating the CPU memory to the GPU memory. So this is kind of a very bad thing to do because it's very slow. Is this traverse move that I showed in the graph before. And finally, we compute this this function importance sample in the GPU, where we specify like how many threads and how many blocks we are given in our hardware. These numbers can be optimized depending on the hardware. And then we run this function in parallel. And finally, you can see these functions which are familiar because we've seen them before. We reduce this long vector in a sum and then we compute the mean. And that's it. And this is the program. How can we improve this? Is just, for example, as mentioned before, we could generate our random variable in the GPU. So we avoid this line, which is slow. But for doing that, we need to use the splitting seed methods, which are for the sake of this paper too advanced. So we just stick with this for now. All right. And yeah, so in practice, this paper is describing three main algorithms, which are advanced, but they're not that advanced, which are the population-based, I think it's called population-based. Oh, this population-based. Yeah, Monte Carlo. SMC, sequential Monte Carlo, and SMC samplers. I think tomorrow we are going to discuss thoroughly the sequential Monte Carlo and how to do parallelization. So I won't discuss this. I will just talk about this population-based Monte Carlo, which is, for the sake of this paper, is parallel tempering, essentially. And this sequential Monte Carlo samplers. Okay, let's start from the first one. So, first of all, we augment our state space from being X. We use some auxiliary variables, so our state space becomes X to the M. Okay, so we have M copies of our state space, and we define a target which is by var of x1, x2, blah, blah, xm, which is just the product from 1 to n of pi I xi. For some, that is pi I. And essentially, these pi I are such that pi m, capital M, is equal to the target. And all the others are kind of approximation of our target. So pi m minus 1 is a close approximation of our target, and pi 0 is something which maybe doesn't have anything to do with the target. Okay. Right. So how do we set up a Monte Carlo method which is on this state space? Is something that we can parallelize, and is also kind of we can use all these copies to help the Monte Carlo sampler to explore our state space. So these copies they must kind of be used to sample from our targets. So for this state space, right? Otherwise, there is no point. Right. So the first step is to define Markov kernels. So let's say that we define Markov kernel I on X, which is equivalent to II. And we can do a first step where we apply these all these Markov kernels to all these subchains x1, x2, xn. So we just apply L1, L2, L3, Ln. And we can apply these Markov chains all in parallel because there is some communication, right? Because these Markov kernels, they are just acting on a subchain, not on the whole chain. So we can do this step in parallel. This is kind of trivially parallelizable. Okay. And then there should be a communication between all these subchains. Otherwise, there is no point of doing augmenting the state space and doing all this work. Then the second step, which is the communication. So we define new kernels, K1, K2, up to K, say, R. Let's say that Ki acts on the indexes say I, and leaves this measure, this marginal measuring bind. So is the I on the J on I. Sorry. So essentially, this kernel is taking some bits of some subchains and is acting on those subchains. Not in all subchains, in some of them. And of course, if these set of indexes are disjoint, then we can also do this step in parallel, right? There is no problem. But the problem is that if these sets are disjoint, then there is no communication again among these sets or these subchains. So the clever thing is to have these sets to change the sets over time. So we can do both parallel. We can do this step in parallel, but also we have communication among all subchains. So we just say that I, which is the whole vector of sets, it's going to be, for example, it's going to be 1, 2, 3, 4. Let's also give a time dependence when t is, for example, even. And then it's going to be 2, 3, 4, 5, etc. until M1 when it's odd. So this is kind of the standard parallel tempering algorithm, where these sets are always disjoint. So we can run with M divided by 2 parallel threads. This kernel K, and that's the step after we just switch to other indexes. So again, there is communication with all the chains after a while. Yeah, after 2 steps. And yeah, so in this way we can run actually the full algorithm in a parallel. And this has been proven to be, well, a very efficient algorithm. Although there are some details which are more theoretical, they don't have really to do with parallelization, is that you would think that at this point you could use, you want to use all the threads that you have available in your GPU. This turned out not to be the most efficient thing. So there is kind of a trade-off between the number of parallel chains that you want to impute and the mixing time of this last component, which is the one that you are interested in. Okay. And I think, is Seth online or?
Not today.
Okay, because he worked on the non-reversible parallel tempering, where this problem was kind of resolved. And then it was kind of useful, I think, to have as many threads as possible in your, at least conceptually.
That's important. If you keep on increasing, it stops.
Yeah, exactly. I mean, probably in practice, maybe you still have some overhead that is increasing, or I don't know. But yeah, in theory, I think for non-reversible tempering, you want as many threads as possible, right?
It's not that. So the thing with the reversible one is that the efficiency increases.
Yeah.
As you increase.
Yeah.
But for the non-reversible, you can prove it's never worse.
Yeah,
but
yeah.
You do have like support type of
Yeah.
efficiency still.
Yeah.
If you learn the pressure distribution.
Yeah.
I think Seth would also say that there was sort of like once you have a certain number of chains, you should start a separate instance of parallel tempering.
Yeah.
So it's kind of a bit annoying to.
Yeah. Okay. So in practice, probably you still want to fix a number which is doesn't go to the.
They have lots of answers.
Yeah. But at least you don't have this deterioration of the mixing time, which is good news. Any question so far?
Actually, can I just
Yeah.
make a comment?
Yeah.
Can we get back to the functional programming?
Yeah.
So what you call the first step here, right, is just a map operation. Yeah, you're just applying a kernel independently to each independent chain.
Yeah.
So that's
Yeah.
the map operation.
Yeah.
But this second step here, where you're communicating between adjacent pairs, that's kind of applying a kernel sort of to two adjacent chairs.
Yeah.
Two adjacent chains. Yeah.
Yeah.
And so this is the situation where this trick of borrowing an idea from category theory and using a co-bind operation on a co-monadic structure comes in. Yeah. So in a pure functional language, the clever way to do this is using co-monads. The second step, I mean, you can do it in lots of ways, but the cunning way is using co-monads, right? So that's where it comes in.
Is it also kind of a map operation?
But it's kind of a map operation, but you're borrowing information from adjacent values. So it's like really applying a local kernel that has some adjacency information.
Okay.
That's why it's not a simple map operation, but it almost is.
Mhm.
And that's kind of what this co-bind is. It's sort of almost a map, but using a little bit of adjacent information.
All right. And so in functional programming, are there like structures which are for this, or for this kind of special mapping where you're using?
Exactly. So it's called co-monad.
Okay, come on. Okay. Right. Yeah. So I guess so. This is the implementation of it. Yeah. A bit annoying. It's true. All right.
Very good question.
Yeah.
So how do you initialize each of those X's? Do they initialize the same or?
This doesn't really matter because eventually we iterate between these two steps. So first step and second step. So like hopefully the Markov chain mixes, and so you would converge to this density pi bar.
Yeah.
So are you asking in practice? How
I'm just wondering if there is like or they just do equal initializations for all of them. I don't know.
Yeah, so I also haven't specified that it's a PI, but PI
is like a flattened.
Yeah, so I think PI X Xi X is could be, I think in this paper they fix it to be pi, and then they just do I over m to the square.
Okay.
So when I is equal to m, then you have pi, and when I is equal to 0 or 1, yeah, it's almost a flat density. So it's a worse and worse approximation of pi. Other things are, if you have a prior in the Bayesian setting, your pi 0 would be the prior, and your pi m would be the full posterior. And in between, you kind of interpolate between those. But there are many ways to interpolate between easy and difficult densities. Yeah, the theory is actually quite involved on this. Going back to your question, the initialization, my experience, I just randomly initialized my algorithm because
Like standard got.
yeah.
In terms of going beyond things that are as general as like how do you initialize any MCMC, I think sometimes you can do things like you run an SMC sample or an annealed sampling once,
Okay.
and then you collect each thing sort of at the temperature.
Okay.
But it's sort of similar in some sense.
Okay.
Like you don't want to have to do a full SMC sample run that solves the problem.
Yeah.
So it's kind
And
of,
that beats the program.
If you reference the sample from the sort of section.
Yeah. Or maybe start from the prior in a Bayesian setting. I think would be a sensible thing to do. Yeah. All right. Any other question? All right. So let's move to the second algorithm.
How do you implement?
Yeah. How do you-
That's not the code for it.
No. This is not. There is no code for actually the other implementation. This is just the. Yeah, I can actually close this page because, yeah, this is just the important sampling snippet of code, nothing else.
So does it actually take care of the use for that moment?
What is there?
I actually, so you typically should do it like 30 cores, right? Like if you have 30 processors, like that's probably plenty. Like you don't need a few thousand.
Oh, here they are. We can have a look, but I think they are using thousands of threads. So what they are taking examples which are artificial. So I can show you the example they are taking is this one. So a kind of a huge multimodal super bit, and they're using m equal to 200. So 200 threads, and they're doing it in the GPU. So your question was this one?
Isn't that you would end up with the issue with regime from.
because they weren't using the non-reversible at the time.
Yeah.
Yeah, it could be the case. Because they're using the reversible parallel temporary, which means they're having too many hooks to go.
Yeah.
Yeah, I don't know.
I guess the point to get like.
Yeah, actually it is that. Wait, this is I think the. Yeah. So, yeah, actually. So it's much larger than what I said before. Yeah. So I'm not sure in practice how many, but yeah. This is a kind of I don't think here they want to make a point of you need to do that. It's just to raise the attention for statisticians and for people working in Monte Carlo simulation that you should think how to parallelize algorithms because it makes sense. Okay.
Setup, but also the swap loops parallel, that's a consequence.
Yeah. So, but these are clearly trivially parallelized, but since these sites are disjoint, also the second step is trivially parallelized. Yeah. Yeah, I guess this is something that has to do with the fact that we're not using functional programming. We need to be careful when, like, instead of moving the chains, which would require to like move memory, a lot of memory around, we just swap index. Yeah, and that's the most.
No, that makes sense. Whatever programming language you use, if your state space is big, right? So
Yeah.
it sounds like the genetic trees, right? You switch the instance because it's much cheaper to keep which index corresponds to.
Okay, yeah, it's in general, yeah. Yeah, and actually these kernels, yeah. So what Sam you meant is that the kernels, what are they doing is trying to swap the states or the index. Yeah, maybe you can mention that. Like the second algorithm is similar in a way. This is a SMC sampler. Where we define again approximation of our target by one by n. How does it work? Right. So let's say that I x is equal to pi like before. So it's a kind of a higher temperature version of our target. Right. So we have again here a state space which is n copies of our original state space. And you can think of x1, xi, I to be up to n to be particles. And we also define kernels, LIT, which act on the ith copy, so on say xi, and leave by I environment. Okay, so this is the setting. Now, what do? Is we just apply the same kernel. So this I is just to say that it's acting on the particle xi. We apply this kernel to all the particles. So same kernel here. Iteration t. We apply this kernel, and this is again trivially parallelizable. Okay. And we start from t equal to 0. So we start from a very bad approximation of our target, and then we move to the next iteration. So we go to iteration 1. The second step is make sure that we actually target the right distribution. So it's a resampling step. And the resampling step is essentially we resample x. Well, actually, the index is I according with weight So from a multinomial distribution, which has weights pi t x1 pi t minus 1 x1 pi t x2 2 blah blah until pi m x1 no pi t percent. Right. So these are just reweighting, resampling particles. So it's killing the particles which are which have low likelihood, and according to this weight, and maybe duplicating other particles. Okay, and we do it for every so for all the m particles. So we keep our m particles, but we kill some of them and we duplicate others. Now, this step in this article, yeah.
What's the difference between IMT here? IMT.
Just sorry, yeah.
Just about like the.
So here I'm resampling this index, not this. Maybe this bad notation, but so we have a particle. I'm just keeping that some of them alive and killing some other, duplicating some and killing some other, and then I have again.
So do you want to write leaves pi t invariant to the random? LIT, say one
Yeah,
line
it is
up,
it is a
one line up. One line up.
ah yes yes.
So it's IT as well as the topic.
Yeah,
Okay.
I was hoping with this. Yeah, thanks. So the index I is where is it? Yeah, it's denoting just the particle.
Yeah, but then it's I is the capital T or something. No, it's okay. I get confused. But now I get it. It's still.
Yeah. Yeah, maybe I feel got a little bit messed up with the link.
Okay. Yeah, I got it now.
Okay, so here it should be by
Capital T.
yeah, capital T,
Staying in the schedule then.
and
Then
well,
you also have it in the schedule on the.
Pi to the little t of the big T
I
squared.
mean, that's if you want to correct it. I think now we all get it. Doesn't matter.
no, but okay, anyway. All right. And in this paper, they actually don't parallelize this step, this resampling step. But maybe we can have a little discussion because I heard that you can do this step.
You can, so you can compute those weights in parallel
Yeah.
easily, right? That's just another math operation, so that one's good. But then how you actually do the resampling in parallel is interesting, but actually Anthony Lee has another paper called Parallel Resampling the Particle Filter, where he has some kind of basic strategies for how to do this. I'm not sure it's the last word on it, to be honest. I think there's probably even smarter things one can do. But yeah, so that paper goes through what the problem is, why it's not completely trivial, etc.
Yeah.
Obviously, you could like faster resample, so you can independently resample each particle here. And that parallel is trivial, but then you end up with a random number of particles, and you get a number of particles eventually diverge, so that's probably not a great idea. So you probably want to keep the number of particles fixed, but then it's not trivial to kind of keep track of everything and sample everything. But you can probably set it up as a parallel scan. I'm not sure that's something you're going to talk about. Or,
Yeah.
Okay, so we'll talk about it tomorrow.
Okay. Yeah, essentially, this is the paper. So there is not so that they do experiments where they compare these algorithms and they show the benefit, and they get a speed up from 5 to 30 times or even more by using the GPU. So it's kind of raising the attention, I think, for us, for people working in this field, on thinking how to parallelize algorithms, which is something that I'm also not aware of. I was not aware of. Yeah, that's it.
Very much.